So in this video, we're going to build off of some previous work that we've done where we looked at the pencil production problem. We went from the problem statement to a mathematical model, which is what we see represented here. And then we also looked at various ways to solve the mathematical model. We've solved it graphically, and we've also solved it with some software tools. And in this video, I want to take it a little bit step farther and enter what's called sensitivity analysis or post-optimality analysis. And that's where you can basically find a little bit more information about the model and the solution without having to continuously resolve the model over and over again with slight tweaks to different coefficients or right-hand side values. And specifically what I want to do is look at this concept called range of optimality. And so the range of optimality has to do with changing the value of an objective function coefficient. So for instance, it'd be something like, let's play around with this 0.41 coefficient in front of XB, which represented the quantity of economy pencils, and see what happens to our model. And so to get this started, let's first just look at the graphical solution, which I've done a little bit of work here just to shorten the length of the video, and also all this work is contained in some previous videos. And so in a previous video we went through and found the optimal solution graphically, and it looks like this, and the optimal solution occurs at the point 1721.7 roughly, and that's how many economy writer pencils to make, and 5102.7 deluxe writer pencils. And this yields a profit of roughly $5,008. And so we ended up at a place like this. And the question that I wanted to ask here is, well, by how much can the unit profit contribution of the economy writer pencil vary and still have the model retain the same optimal solution? And so basically we want to make sure that the model still stays at that point right there, and we'll start to vary that 0.41, I believe was the value in front of the variable representing economy writer pencils, and see how much we can vary one way or another way and still stay at this point. And one of the things you'll notice about this is that's going to be dictated largely by the slope of the objective function line, which is red in this case. So with that being said, let's go ahead and move over to my scratch pad here. I've done a little bit of work as well, basically recreated the feasible region, and then I've also done some work to determine the lines associated with the different boundaries. So in green you can see this is the line for the shaping constraint, and in red is the line for the assembly constraint there. And again, what we're trying to do this maybe in white, is look at the feasible region right here and want to start varying the coefficient in front of that economy writer pencils. And so one of the things we can do is say, okay, the objective function line currently sits something about like this. And as long as that objective function does not go beyond this line here or this line here, as we modify the slope, then we'll still retain this point as the optimal solution. And essentially what we'll see happening is we're going to start to vary the slope or kind of rock that line this way about that point. That point will almost act as a pivot point for us. So we just need to find the bounds by which we can move that. And maybe the first way to do that is look at the slopes, and the slope of this line here is that value here, and the slope of this line here is this value here. And so we need to say, well, let's constrain the slope of the objective function line such that it is between those two values. And so I'll start with that down here. So we would say something like the -8/10 is the more negative of those two slopes, so it's a -8/10. So be less than or equal to, I will just say slope here for now. That's the slope of the objective function. Must also be less than or equal to -5/35. Okay, so that's good, but now we need to relate the slope back to the coefficients in our objective function. So if we want to think about that, our objective function we could say is the profit is equal to 0.41 x sub b plus 0.84 x sub d. But I want to generalize this a little bit, and so what I will say is, instead of writing it like this, I'm going to first write it as some value times x sub b plus some other value times x sub d, where alpha and beta are our two coefficients here. And one of the things you may be looking at is, well, that's just a linear equation. So let's go ahead and put it in a form similar to what we've got up here, where our vertical axis is x sub d and our horizontal axis is x sub b. Kind of thinking of a y equals mx plus b scenario here, where the y is represented by x sub d and the x is x sub b here. And so we can do that with just a little bit of algebra and say x sub d is equal to 1 over beta times my profit minus alpha times x sub b. And let's just move our beta in here and readjust things a little bit. So I'd have negative alpha over beta times x sub b plus p over beta here. And again, this is now y equals mx plus b, where the slope is this guy right here. So using this information of this as the slope, we can now go ahead and plug that into our inequality we've got over here. So taking this, bringing this over, we can now say negative 8/10 is less than or equal to negative alpha over beta, which is less than or equal to negative 5 over 35. Multiply it all by negative 1, so we can flip the inequalities. And so at this point, we would be able to ask the question, well, we want to vary either the coefficient in front of x sub b or x sub d. In this case, I think we are wanting to vary the coefficient in front of x sub b, so we'll say, let's let beta equal 0.84, and then we could solve for alpha in each case. So I'll say alpha here greater than or equal to signs. If I take 0.84 and multiply by 8/10, I believe that should get us close to, let's see, 0.84 times 0.8, 0.672. And similarly, 0.84 times 535 is 0.12. And so at this point, we've achieved what we were looking for in some instances. Basically, we have obtained what we call the range of optimality. So I'll write this out down here. Range of optimality for x sub b. And it is the interval 0.12 and 0.672 here. It should be the closed interval including those two values, since we had less than or greater than or equal signs here and here. And what that actually looks like, if we go back to the Jupyter Notebook graphically, is, again, what I talked about earlier, basically this idea of the objective function pivoting around that optimal solution point. And so that's what we have here. In this case, we've got 4 different values for that alpha coefficient, all the way from the 12 cents, which is basically the low end, up to the high side of 67 cents. It was actually 0.672 when we worked it out, but we just put 67 here, and a couple values in between here. And one of the things you can see is at the low end and the high end, basically we end up with this case where you have alternate optimal solutions where the objective function line is running parallel to either one of the constraint boundary lines here. And so hopefully that helps you to visualize and think about what the range of optimality is actually looking like. The other thing that is worth noting, so I come back here, is that this can actually be done for you as you run sensitivity analysis in a certain software package. So in this case, I'm going to open up a solution of this problem using MS Excel, and when you run the MS Excel solver, you can have it generate certain reports, and one of those reports is the sensitivity report. And so I'll go ahead and show that now. In this case, it is here. The economy rate or quantity was represented our x sub e decision variable. And the way they talk about the range of optimality is through these values right here. And so we went ahead and calculated strictly the range, the top and bottom, but they give you the degree allowable increase and allowable decrease from the objective coefficient. And so I can show you this very simple translation here. If I take that value 0.41 and add the 0.26 to it, I get my 0.67, which was our upper bound. Similarly, if I take the 0.41, which is the objective function coefficient, just truncating to 2 decimal places here, and I subtract the allowable decrease, 0.29, I end up at my 0.12, which, just to show, are the exact two boundaries that we calculated here using the kind of longer manual method. And so hopefully that sheds a little bit of light on the portion of the table that you're seeing in the sensitivity report in MS Excel as well. And so with that being said, I'll go ahead and close out our video. And again, thanks for watching, and hopefully this helps you gain a little bit more understanding of the area of sensitivity analysis when you're looking at linear programming.